All right, so because I'm not in today, I'm going to go ahead and just make a little video. But basically, our goal today is to learn how to calculate elastic potential energy. So we've used conservation of energy equations, you've learned the equations for gravitational potential energy and for kinetic energy, and today we're getting one more equation, and that's the equation for elastic potential energy. So the equation, it looks like this, right? So the EPE, this just stands for elastic potential energy. And the equation is 1/2 times K and then X squared. We need to talk about sort of what this K and what this X really mean, right? So the K is basically a measurement of the stiffness of the spring. And this could also be like a rubber band. And this is basically a measurement of how difficult it is to stretch or to squish the object, right? So like, for example, right, there's like different kinds of rubber bands. So, right, maybe you've used a rubber band, like if you've ever been at the grocery store, like sometimes they have these really, really heavy duty rubber bands that are used to like hold like broccoli or something like that together, right? If it's really hard to stretch, the K value would be really big, right? And that's because the more you stretch it, the more energy it stores. Whereas like a really kind of a weak rubber band, right, one that you might find for like office supplies, would have a smaller K value. Same thing with springs, right? So if you're dealing with like a really weak spring, like something in a mechanical pencil or something like that, the K value is going to be really small. But if you're looking at like a garage door or something like that that has really heavy duty springs to help make it work, those springs would have a really big K value. And so in general, if it's harder to squish something or stretch something, the K value is bigger. The X here, the X is the distance that the spring is stretched or compressed. So in general, springs or rubber bands will have sort of an equilibrium position, right? So like in this case, you can imagine this spring is just here and it's not stretched or compressed. This is where it would sort of naturally rest. In that case, the X is 0, right? So if X is 0, it's not storing any energy. And X is a measurement of how much we stretch it from that position or squish it in. So for example, if you were to squish this thing, right? So if this ball were moved to here, for example, the spring would be squished about that much, and that would be X. And you can just take X to be a positive number, right? So don't worry about direction, just think of it as the stretch or the compression distance. But even if you did use a negative, right, you're squaring it anyway. So it sort of doesn't really matter. In the case of some things, they can only be stretched, not squished, right? Or vice versa, I guess. But if you imagine like a rubber band, right, you can stretch it to store energy, but you can't really squish a rubber band to store any energy, right? So that X there is just the stretch distance or the squish distance. It's not the total length of the spring or the total length of the rubber band, right? So let's imagine that you had like a rubber band or something hanging from like a hook on the ceiling, and this is where it hangs naturally. And then let's say that you you hung something off of it, like maybe a little weight, right? And then the rubber band stretched down. So in this example, right, the X would be how far that rubber band stretched. So in this example, X would be that distance right there. All right, so how much it's stretched from its unstretched or equilibrium position. So let's go ahead and just look at a couple quick examples. So here, I'm going to grab my calculator, so maybe just read that question while I grab it. All right. So, right, we've got a spring, we know the stiffness constant, right? That stiffness constant right there, that's our K. And it's giving us the compression distance is 0.1 meters, so that's our X. And it's asking us how much energy is stored in the spring. So this is just sort of a straight up application of the equation, right? EPE equals 1/2 KX squared, right? There we go. And then we just plug in the numbers, right? So the K is 500 and the X is 0.1 there. And then we're just plugging it in. This is EPE. So 0.1 squared should give me 0.01. I'm literally just typing this into my calculator right now. This is giving me an EPE of 2.5. I don't like that 5 very much. 2.5 joules. Done. Okay, so this is part A. And for question B, right, how far would I need to stretch it to store the same amount of energy? So in this case, it's telling us that the spring was compressed. But remember that the x, right, could be either the stretch distance or the compression distance, right? So in this first example, it was compressed, but if we stretch it the same distance, right, if we stretch it 0.1, x would still be 0.1. So the answer would be the same, right? It would be 2.5 joules. All right, and also just as a side note, and I don't want us to get too focused on this, but the units for spring stiffness constant or spring constant, that K value is newtons per meter, right? I think I have this written here, right? And that's because if something is, this is basically how hard it is to stretch it per distance, right? So if you need to apply 100 newtons to stretch it a meter, it's a stiffer thing than if you need to apply, 50 newtons to stretch it 1 meter. So this is like the amount of force it takes to stretch it a meter. That's where this unit comes from. And the higher this number is, the higher the spring constant. Okay, let's look at another example. Okay, so a 5 kilogram mass is placed on a spring of stiffness constant 2,000 newtons per meter. If the spring is squished down a distance of 0.35 meters, should say from its equilibrium position, what maximum height will the mass reach above its starting position if it is launched up in the air? All right, so basically what we're doing here is we're squishing this down and we're shooting it off the spring. So let's first just think about the types of energy we have here. All right, so initially we've got spring potential energy stored in the spring, and at this later time the mass has been shot up in the air, and at this highest point it's not moving anymore, so it's got all gravitational energy. So we've got all spring energy turning into all gravitational potential energy. So we have EPE turning into GPE. Okay, so let's go ahead and work out our equation. So I'm going to switch to blue. Right, our equation for elastic potential energy is 1/2 kx squared. So that's the type of energy it has at the beginning. And then later when it's up in the air, it has all gravitational potential energy, which is mgh. And we're looking for the height, right? That maximum height that it's going to go to. So we're looking for the h. So now we just have to plug in our numbers. So 1/2 times 2,000 times the compression of the spring, which is 0.35 squared. And this is going to be equal to the mass of the object, which is 5 kilograms times 9.81 times the height. That's what we're looking for. So I'm just going to go ahead and plug the left-hand side into my calculator, see what I get. So it's okay. So I'm getting 122.5 on the left-hand side. Yep. And then on the right-hand side, I'm going to do 5 times 9.81. And that gets me 49.05 times h. And then to solve for h, I can divide both sides by the 49.05. So 122 divided by 49.05. And this is giving me 2.49 meters is equal to my height. Cool. So that's about it. For the rest of class, there should be a handful of elastic potential energy questions. I think it's one sheet front and back you can work on. So I'd like you to work on those, and I'd also like you to make sure that you've looked over all the solutions for the questions that were due today. And if you have any questions on those, I really encourage you to send me a quick email if anything in the solutions seemed confusing. So I think that's about it, and good luck working on these. And if you feel stuck, make sure to email me and just like be ready to ask any questions you have at the beginning of next class. All right, thanks guys.